Hi class. In this particular class, this is topic number 3. In this topic, we're going to talk about, in this particular class of the topic number 3, we're going to talk about dimensionless analysis. Dimensional analysis is very, very important in aerospace structures. It allows us to compare one aircraft with another aircraft. It get different dimensions, different properties, uh, and compare with another one with a different dimensions. And the idea is that what we look at it, we look for is the dimensionless quantities for that. So to better understand what the dimensionless quantities are, we can think about, probably heard about Reynolds number, even the Mach number, right? Mach is nothing else than the speed of the aircraft divided by the speed of sound. That's a dimensionless number. Coefficient of lift, coefficient of drag, and the list goes on and on and on. To better understand that, let's just lay out the groundwork and work our way up to drive these equations. So to do that, one theorem that's very, very useful in our analysis is called the Buckingham Theorem. That particular theorem, let me write that down for you. It's called the pi Buckingham, theorem. Okay, and basically, it is very helpful. This theorem is very, very helpful when we have a series of parameters that are involved in the computation, such as forces and moment. That will help us to relate one parameter to another. So let's write that down. When there are a series of parameters involved in the computation of relevant quantities as for an example, maybe forces, moments, often one can find combinations of these parameters. And as I just mentioned to you, what we are very, very much interested, we want to know many of these parameters, especially in the analysis of aerodynamic forces. So what we are interested is in the aerodynamic quantities, well, if I can write it, aerodynamic forces and moments. That's where we are very much interested in applying all these properties. So to understand that, let's consider the following. Let's consider the case where a arbitrary function, we don't know what that function is. Let's suppose that function is that property f is a function of density, viscosity, speed, length, dimension A, temperature, pressure, shape, and the list can go on and on and on and on. Note, just for clarification, gravity is not significant. So you might think, why? Gravity in general, gravity might change, might have slight changes as we go at altitude h above the sea level, but however, it's not going to change that much. And we are really trying to analyze what happens at my aircraft if I take a small picture in time. So my plane is moving and I freeze the moment in time, take a picture, and try to analyze what happens to it. So in that particular instant, the gravity is really not going to play much of a role there. Okay, and the theorem, the Buckingham theorem, basically based on the principle of homogeneity. So the Buckingham theorem is based on the principle of homogeneity. Okay, and basically this base it says nothing else than the members of an algebraic equation of physical significance must all have the same dimensions. Okay, that's what this principle states. Let's work with a simple example. Okay, to kind of lay down the groundwork to understand what we're saying. For clarity purposes, again, this is not a full example, just to lay down the groundwork what we're doing. Let's suppose I have the case of F is equal to mass times acceleration. Okay, so we know that mass is a property of M. Let's say A is a property of length over time squared. Okay, then what we can say is that my force is nothing else than mass divided by length over t squared, or is nothing else than mass L to the minus 1, t to the minus 2. So this is basically the basics of what we are trying to do. Take some standard quantities and find what the coefficients are that can basically represent my function. So I could say in this sense, I could say this is a function of mass, it's a function of length, it's a function of time. Okay, so force is a function of these two, and this is how they are related to each other. I could do something like that. Let's say for an example, and let me use another example. In another example, in this particular example, let's suppose we are working with a shear force, and the shear force is viscosity times my velocity times the gradient. Okay, so in this particular problem, what I'm going to have is, I'm going to have the following. So the viscosity is used typically is in a function of kilogram mass times seconds, nothing else than mass, length times time. My displacement in u is nothing else than meters, so that would be L, and my distance y is also measured in meters, that would be L. So I could say that tau is equal to mass over L times time, L over L, or this is the same as mass L minus 1, T minus 1. So this is how this dimensional analysis actually works. What we are trying to do is we are trying to find some standard properties and see how this is a function of. So in this case, you could say your shear is a function of mass, a function of length, is a function of time. We don't have to worry, we don't care for the coefficients. The coefficients are given by this. So in a very, very, very general sense, what we could say is that in general what we could have is a force, the aerodynamic force F, that would be, we are adding all this, we can add many of these things, many forces, and they all would be a function of letter A, density B, maybe velocity C, length D, A, E, and basically this goes on and on. And if you were to try to expand this, right, and we were going to say, for instance, all of this, okay, the dimensions of F, this is dimension, okay, that would be, find the dimension of the summation of I to N, that will be Ci rho A mu Vc L over D, and note that I have dropped, the speed of sound from the equation because what we are doing is, we are working with incompressible flow, and this is a consequence of incompressible flow. Okay. Compressible flow assumption. Okay. So if I'm going to start doing the dimension analysis of this whole thing, it will look something like this. First of all, the very first thing I have to keep in mind is the dimensions of F. Okay. Remember, this is force, this is mass times acceleration. So this is nothing else than mass, length, t squared. So this is the left-hand side. And my right-hand side then will look something like this. I have the first term, let's say only one term. I have mass, length, q to the power A. And my viscosity is mass times L divided by time. And then my velocity is nothing else than L divided by length divided by time, and my length is L over D. So now what we need to do is we need to rewrite all this equation to find these coefficients. So the idea is to compare the left-hand side with the right-hand side. To do this, I'm going to rewrite this whole equation in the following form. Okay, so this side is equal to MA L3A. Doing a little bit of algebra here. MB LB TB multiplied by LC TC LD. Okay, so let's further simplify all this. Let's write it all together. And I can do that by saying take all the masses together. If I take the mass, I have mass. This is A plus B. Let's take all the L's together. So I have L let's start with D minus 3A minus B. This is this quantity right there. Okay, and also I have to add plus C, this C over here. The last quantity is T, and T is nothing else than T is minus B minus C. Okay, so now what we're going to do is we're going to compare these coefficients with these coefficients. And what you can immediately see is I have basically this is 1. So this has to equal to 1. This is also equal to 1. So this has to equal to 1. And this has to equal to minus 2 because of this. Okay, so basically I'm going to have a set of equations which I now need to solve and I would like to solve. So this is what I'm going to do next. So we know that A plus B is equal to 1. A plus B is equal to 1. We know that C plus D minus 3A minus B is equal to 1. We know that B plus C is equal to 2. Again, this comes from comparing my left-hand side to my right-hand side. Okay? So now we start the process of finding these values. And what you can see is, if you solve for these equations, you can see that A is equal to 1 minus B, B is equal to B, C is equal to 2 minus B, D is equal to 2 minus B as well. So the entire equation then basically becomes as follows. So if I just take one coefficient, I had A, B, B, sorry, mu. I had B, C, and I had LD. So if I replace these values there, what you find is, remember, this is summation. It was summation, I, and this was all equal to F. So you have rho 1 minus B, mu B, B 2 minus B, and this is 2 minus B. Once again, the way I solved this was solving this equation and leaving one unknown. Okay, I intentionally chose to leave B as my unknown. So this was going to be, I wanted to express everything in terms of B. You can have express everything in terms of A. You could have done anything different. Okay, so but I decided to do it like this. So if I can rearrange this equation now, if you would, you can see I have a square, I have a square, I have a square. So I'm going to go into next page. And so my F is equal to summation of CI. I have rho, okay? So let me just bring this up. Let me bring this equation. here. So we can follow this. It's easy for you to follow. So this is B, so it goes 1 over rho B. Let's put it in the parentheses at the bottom. This is mu B, so keep the mu B together. Now we have V squared, and we have 1 over VB, and we have L squared, and we have LB. So it's convenient to write it like this. And now realize all the components that are not a function of B. This is not a function. This is a constant exponent. These are all constants. So therefore, what I could do is I could take it outside my summation. So now this becomes L squared times rho V squared times L squared, and summation of Ci mu rho V L to the bth power. Okay, and if you realize, if you recognize that from your this term right here is nothing else than the Reynolds number. Okay, so this is the Reynolds number, and the Reynolds number is very useful in fluid mechanics and aerodynamics because it helps us to understand how is the flow of my fluid. And the Reynolds number is typically given like this. It is given by rho V L divided by the viscosity. That's the definition of the Reynolds number, and it's going to help us to tell if my fluid is turbulent or is not turbulent. In general, if I'm going to give you a full definition, this is a very important number, and we see this all the time. Reynolds number is nothing else than the ratio of inertia forces divided by viscous forces. Okay, so this is nothing else than motion dominated. And this is nothing else than viscosity dominated. Okay. So just like the Reynolds number, you can see it's a non-dimensional quantity. Okay, because it's force divided by force. And in the same way, we could do this in many, many, many different problems, and we can find these non-dimensional quantities. So just to write this down, note that this is a non-dimensional quantity. Okay. And we use this very, very, very often in aerodynamics. This term and many other terms, which we'll derive it as we go along. And so, therefore, what I could do is I could say my entire force is equal to the summation of I times Ci mu rho L, and this is mu. And remember, just remember we had this term right here, rho V squared L squared, so that has to stay there. rho v squared L squared. And we can say this is equal to some coefficient of f. You see, I got an f here. So then what I typically do is I'm going to make a subscript f at the bottom where I'm saying this coefficient is related to this. Okay? And obviously multiply by L squared. So what I'm saying is whatever this is somehow it's related to this, and this is how it relates to. But I have is a function of a non-dimensional quantity CF. In this context, I could just say, and it's very convenient to write the equation like this, say this is rho v squared. This is nothing else than area, and this is CF. Okay, so what you're saying is, what you can try to do in this problem is, if you have some way of finding CF as a function of the Reynolds number and for the same shape, then you can find your force. And this is typically done using testing. So we find this using testing, maybe wind tunnel, or nowadays we use CFD, computational fluid dynamics. So what you're basically saying is, given shape, remember it's a function of the Reynolds number and the Reynolds number. We can find CF and therefore find F. Okay, so remember again, this is this term right here is the Reynolds number, and this whole thing is what we're going to call CF. Okay. And there are many other quantities in aerodynamics that we are interested. As for an example, the lift itself, we are interested in lift, and we can show that lift is equal to 1/2 rho v squared times the area is equal to CL. Okay, and this is the density, the stream density, air density. This is the speed of aircraft, which is also the speed of the wind. This is the wing area. This is both wings, not one. And so therefore, this is what we call the coefficient of lift. This is called the coefficient of lift. Okay. Similarly, we could have the same thing having the drag. Drag is nothing else than D is equal to 1/2 rho V squared S times CD, and this is the coefficient of drag. Okay, and these properties are the same as before. I can also have my moment, my aerodynamic moment, and the aerodynamic moment is given by 1/2 rho V squared wing area times my mean chord times Cm. Okay, this is the mean chord. We will go over that in a moment. What is it? This is the coefficient of aerodynamic moment. Okay, that's the coefficient of aerodynamic moment. And in the same way, we could find many other properties itself, which are very, very useful. Before we move on, there are a couple of things I do want to define. And let's have the case of the wing of an aircraft. Okay. And we're going to talk about these a lot. So I think it's worthwhile to spending a little bit of time for the wing. First of all, the cross section of the aircraft is called airfoil. Airfoil is the cross section of the wing. I can make a section cut. So if you may, I can take a small section cut anywhere. That's the airfoil. The distance from the trailing edge, from the leading edge to the trailing edge, this total distance is typically called C. This is the chord, and we can say this is the mean chord of the entire aircraft. And then this distance from here to here of the tip of my plane, this is called B. This is nothing else than the span of my aircraft. And then the area of my aircraft is equal to, okay, and then if I want to find the span area is nothing else than as you can see, just give me a minute. I'm having trouble here with my pen. Span area is nothing else than B times C in a rough sense. Another quantity that we use a lot is the aspect ratio. The aspect ratio is given by AR, and it's nothing else than my total span squared divided by my span area, or B over C, because this is BC and BB's cancel out, you get this. These are some, these are important dimensions that we're going to use this a lot, and so I think it's worth to define these right now. As we move on, we'll keep defining some more, but this is the aspect ratio of the aircraft. Okay, so this class was mainly, the whole purpose was to give dimension analysis. I know it looks a little bit abstract, but we will, as we move on and we keep on using this a lot, you will be a lot more clear. In the next video, you have a couple of examples where we expand on the dimension analysis and how this really works.